So last time we were talking about some asymptotic properties, in particular the long-run variance. I would like to continue, and today what we do is we repeat the simple linear regression. Okay, so you can solve your basically your next assignment. This will be about it. So also this is an example. Okay, so what I'm talking about is, and we just continue. Okay, so we have basically the autocovariance, right? Remember the autocovariance? Okay, look like this. And the autocovariance has been the covariance of yt and yt plus h, which is basically the expectation of the product minus the product of the expectation of the two. Okay? So this is the expectation of the product minus the expectation of the two. Minus the product of the expectation. There you go. So this is going to be it. Right, so here you have t, and here you have plus h. Okay, so now I'm going to call this, okay, so assume that y is stationary. So if y is stationary, let's say, okay, so y is stationary, okay, then of course the autocovariance is not dependent on time. So basically I'm going to call this gamma. Okay, so for the correlation I use rho, but for the autocovariance I use gamma. So gamma at time, okay, so gamma of the process, let's say y, for the time lag h. So it only depends on the time lag, but not on, basically not on the time t itself. Okay, so here you have t plus h. I don't know whether or not you can see this properly. Okay, so here you have t plus h. Here you have t plus h. So that's the one. Okay, so this is just, you know, a notation that I use here. This is the theoretical one, and the estimate. Okay, so the estimate, I mean, what we have is basically we take the autocovariance from the sample. Okay. Now we have to be careful a little bit, because let's say we have a sample of following processes. Okay, so let's say we have y1, okay, so y2, okay, and so forth, and yt, capital T. So that's the sample. Suppose that we have something like that. And we estimate the autocovariance, okay, for time h by using the following expression. So what we have here is we use basically the sample analogs here. Okay, so this is going to be as follows. So here you have 1 over t, capital T namely, because that's the sample size. And then the covariance, okay, so we have, of course, you replace basically the expectations by the mean. Now, if you replace the expectations by the mean, then basically you would have that what here is yt, right, minus y bar, which was the arithmetic mean, maybe you remember, and you multiply that by yt plus h minus y bar. Okay? Now, that's just basically replacing the theoretical mean by the sample analog, right? But the thing is this, okay, so since you have your time lag t plus h, okay, so if you say that t starts at 1, okay, so that's going to be the first observation basically, then it doesn't stop at capital T, because if you have capital T for, okay, so if t is equal to capital T, then basically you have capital T plus h, but we just have t observations, right? So capital T namely. Okay, so we don't have like t plus h observations. So the sum stops at t, capital T minus h. Okay, so that's going to be the last one. All right. Okay, so that's basically how it's done. So this is the estimate of the autocovariance. Okay. Now, for the autocorrelation, okay, so, I mean, basically this is the autocorrelation from a theoretical perspective, okay, for a stationary autoregressive process, okay, it's going to be as follows. So from the theoretical perspective, I mean, you have all seen this. Okay, so y is stationary, so this is going to be the autocorrelation of the stationary process. So here you have the covariance, or let's say autocovariance, okay, divided by the product of the standard deviations, right? Now, if we divide by the product of the standard deviations and the process is stationary, then the product of the standard deviations will be the variance of the process. And the variance of the process is basically obtained if you put for the autocovariance, if you set h equal to 0, so that's going to be it. Okay, so this is basically the autocorrelation, provided that the process is stationary. Okay, so let's say I will add this here because that's not clear from the notation, so y must be stationary here as well. Okay. Again, the autocorrelation is equal to the covariance divided by the product of the standard deviations. Since the process is stationary, the standard deviations do not depend on time, so they are all equal, right? And so therefore, the product of the standard deviations will equal to the variance of the process. And the variance is of course obtained if you, for the autocovariance, you set h equal to 0. That's going to be it. Okay? Now the estimate is going to be, okay, so just replacing the theoretical ones by the sample analogs. Okay? So basically the estimator for the autocorrelation, okay, is going to be just, you know, the estimator of the autocovariance of the process, right? So you have here you have the autocovariance, and here you have the estimator of that divided by the estimator of the variance. Okay. So that's how you would do that as well. Okay, or you can do that too. Okay. Now, of course, we basically can show that these estimators are both unbiased and consistent. So we do not look at the third properties. And basically, what it means is that it converges, you know, the theoretical, or let's say the theoretical analogs are the limits of the corresponding estimators. Okay, so the estimators converge in probability to the theoretical analogs. That's quite obvious. All right. Now, let's just recall, you know, the formulas for the linear regression model. Okay, so what I'm doing is here the linear regression. Okay, so this has nothing to do with autoregressive processes, or time series, or whatever, because this is just a generation what I'm doing. Okay. Okay, so here in this case, the variable y, okay, it's not necessarily a stochastic process. This is going to be the dependent variable. Okay. Okay. And the variable x, okay, so we start with a simple case, is going to be the explanatory variable. Okay. So the explanatory variable is basically the variable that explains the other variable. Okay. So here in this case, I mean, the simple linear regression is basically, behind the simple regression is basically the following model. So here you have basically yi, so this is going to be the ith observation, okay? And let's say this is equal to a constant plus a slope times the explanatory variable, okay, so, or to be precise, times the ith observation of the explanatory variable, plus you have the disturbance term, okay, so epsilon, okay, is some noise here. Okay, so that's basically the linear regression model. And here you have from I is equal to 1 till I, okay? So that's how it's going to be. Okay, so this is the special case, and we're just focusing on the simple regression here. Okay, because that's what you're going to need, and then you can easily extend this for multiple regression as well. Okay, so that's probably something you've seen before. Okay, so here basically, what you have is here you have x, okay, and here you have y. And basically you have like, you know, some kind of patterns here, maybe or maybe not. I mean, who knows, right? So these are, okay, let's say the observation points, and what you want to figure out is basically the regression line. Okay, so this is the regression line basically. Okay. Right. Now you basically want to have an estimator for that. So the equation for the regression line will be y hat equals a hat plus b hat times x, okay? And a hat and b hat are the estimators, okay, of a and b, okay, right? So that's supposed to be clear here, okay? So this is, a hat is the estimator of the constant, okay, and b hat is going to be the estimator of the slope, okay. Now I'm going to define before I give you the ordinary least square regression model, because I think you should have seen this, but of course you have the arithmetic means, okay, so basically, I mean, x bar is going to be the arithmetic mean of x, okay, so that's something we have probably seen before, okay, in different contexts. Alright, so and then you have, of course, y bar, okay, it's just going to be the same thing, but do this anyway. So here you have the observations of y, you sum them up and you divide them by the number of observations, okay, depending on what you have basically for the explanatory variable, or basically for the dependent variable. Okay, so y is the dependent variable and x would be the observations of the explanatory variable. Okay, now what you also need, and this is what you may have to consider, okay, so I'm calling this s of x, okay, so s squared to be precise, this is going to be the empirical variance, okay, so this is the empirical variance of x, and what you do is, I mean, there are multiple formulas, but I'm taking just the second one, the mean of the squares minus the square of the mean, maybe remember that, okay, so the mean of the squares is going to be, what I mean by that is basically you take the squares of the observations of the explanatory variable, you sum them up, and then you divide them by n. Okay, so this is going to be the mean of the squares, right? Okay. I mean the squares of the explanatory variable, to be precise. Okay. And then you subtract the square of the mean. Okay. And then you're going to get the empirical variance. Okay, so this is the empirical variance, this is the square of the mean, right? So you probably have seen this before, right? Okay? And for y, it's going to be the same. Okay? Just all I'm doing is replacing the observations of x by the observations of y. Okay, so then you can add this. This is going to be the empirical variance, okay, of the variable y. Okay, again, same thing, mean of the squares minus the square of the mean. Okay, we'll later have a little example, so you'll help me out, hopefully. Okay, now, of course, you have also the covariance. Okay, so for that, I'm going to use, okay, so this is, I mean, this is a notation that you're familiar with. Okay, and since I don't have time series, or not necessarily time series, I'm taking something else. Okay, so I'm using it here for the autocorrelation. I use that notation, and for the autocovariance, I use that one, gamma. But this is not a time series, so there is no such thing as the autocorrelation, not necessarily. Okay, so this is going to be the empirical correlation. Okay. All right. So and you could do this similarly. Okay, so just replacing by the sample analogs. So basically, what you do here is, okay. So the mean of the products minus the product of the means. Okay, so here you have 1 over n times the mean of the products, okay, xi times yi, and for y is equal to 1 to n, minus the product of the mean. This is going to be the empirical covariance. Alright? I think that this is supposed to be clear, right? Okay, So now, and for the least squares estimator, okay, so this is just a remark, so I'm going to summarize that. Okay, so these will be the ordinary least squares, okay, so OLS, you've seen this, right? Ordinary least squares estimators, okay? Okay, now starting with the slope, okay? You got the slope or the estimator. If you take the covariance and you divide it by the variance of the explanatory variable, okay, so the covariance divided by the variance of the explanatory variable, and the intercept will be equal to y bar minus b times x bar. Okay, so here you have basically, I mean, here this is the slope and this is going to be the intercept. Okay, so that's how you would get them. Okay, this is not difficult, to be honest. Okay, all right. Now there are some basic properties that these things have. I mean, of course, I'm not going to derive this. Okay, so I think you have seen this before, right? Okay. Now, what are the basic properties that that you would have here? I mean, the equation of the regression line. Okay, so this will be the regression line. So I would add this here, or the equation for that is basically, okay, so I'm using y hat equals a hat plus b hat times x, as you've seen this before. And of course, y hat is not the same as y, okay, because y are the observations of the dependent variable, and y hats are the estimates of the dependent variable, or if you use another interpretation, these are the parts of the dependent variable that can be explained by basically by the others. Okay, so let me just use a different notation here. So this is the model. Okay, so this is the regression model. So here you have, okay, so a hat plus b hat times xi plus epsilon I, okay, so where basically I goes from 1 till n, okay, and this is this part here, okay, so this is basically, and I call this y hat, okay, so this is the explained part of y, so this is the part of y that can't be explained by x, okay, right, so this is the explained part of the dependent variable, okay, or here in this case, in particular of the observation, okay. So here you have yi. So this is the part that can be explained by that, okay. And the other one is, of course, this is the residual part, okay. So this is the part, of course, I mean, you can split it up. This is the one that cannot be explained, okay. So this is the unexplained part, okay. So this is, okay, so unexplained part of yi. So here you have for observation yi. Okay, so this is the ith observation, and you can split it up in two parts. Okay, now the first part will be the explained part, and the second part will be the unexplained part. Now, based on the ordinary least square estimation, you want to keep the unexplained part as low as possible, because you want to have a straight line which best describes the linear relationship between the two variables. Now, meaning that if you want to have a line that best describes the relationship between the variables, it means that the explained part should be large as possible, or other, I mean, similarly, you would say that the unexplained part of the variable would be as small as possible. Okay, so there shouldn't be not much left which is not explained by it. Okay, and that's what the ordinary least square regression is based upon. Okay. Now, interestingly, you would have here basically that, okay, so this is going to be some properties that we're going to discuss here. Okay, so the first property is that the arithmetic mean of the total part of the observations, y, which is the dependent variable, is going to be the same thing as the arithmetic mean of the explained part. Okay, again, so the arithmetic means of the two are equal. Okay, now by that I mean basically the arithmetic mean of the sample that you would get if you put basically the observations of x into the regression line that you were calculating before. Okay, so this is basically what you would figure out. Okay, so that means that basically the sum of the residuals, okay, sum of the residuals, or let's say the mean of the residuals, okay, you can also say that, I mean, this is similar, the mean of the residuals must be equal to 0. This is a consequence. Okay, so basically the regression line is constructed in such a way that the residuals sum up to 0. Okay, now that's going to be the first property. Again, so it doesn't mean that they are basically that the total parts of the observations of y are equal to the explained parts of observations of y. This is not going to be the case. Okay, but it means basically that, I mean, that if you sum them up, then it's going to be equal. Okay, so they basically cancel out. Let me just show you here in this picture what I mean by the explained part and the unexplained part here. Okay, so that was basically the picture, and I'm using, let's say, using an observation that I'm going to take out here. Okay, so that's, okay, so the observation, let's say, that I'm talking about here, so that's the one. Okay, so suppose that here you have, let's say, xi, and so this is what you have, all right? Okay, so that's the point that you observe. And here you have the observation yi. Okay, so this is the point that you observe. And now if you put that expression xi into the regression line, then you're going to get this observation, right? So that's the one that you're going to get. It's up here. Okay, that's the one. And that is, of course, equal to yi hat, right? So this is the explained part of that. Okay, because that's the one. That's the basically that's the expression that you would get if you put xi here. Okay, so if you put xi into the regression line, and you would get this observation. All right. So, and of course, the difference between the two. Okay, so that's the difference. This is the unexplained part. Okay. Now this means that here in this setup that the sum of the unexplained parts are going to be 0. Okay. Sometimes the difference is greater than 0. Sometimes it's less than 0. But if you sum them up, then it's going to be 0, of course. Okay. And that's what the theorem is about. So that's what the statement is. I mean, this is relatively easy to prove, so we're not going to go, I mean, not going to consider that any further. Again, I assume that you already had this somewhere or seen this before, so we don't need to talk about it. Okay? If you want to have an example, then you can check out for yourself. And the second part is basically this is called the decomposition of the variance. Okay? Okay, and the decomposition of the variance is basically as follows. Okay, there is basically also a relationship between the sample variances that you would have here. So namely the total variance of the dependent variable, okay, so that's the total variance of the dependent variable, is equal to the sum of the variances of the explained part. So what you would do is basically you would take the variance of the explained part, and then this the variance of the unexplained part. Okay, so these absence here. All right, so the variance of the total variance of the dependent variable can be decomposed into variances, maybe the sum of the variance of the explained part. This is the, or I call this the explained variance. Okay, this is the explained variance. Okay, and the other one is the residual variance, or you can also call it the unexplained variance. Okay. Okay. Or you call this residual variance. Okay. Meaning that this is going to be the sample variance of the residuals. Okay. And what you see here on the left hand side, this is going to be the total variance. Okay. So the total variance can be decomposed into the explained variance. The explained variance is, of course, the variance of the explained part plus the unexplained part. Again, so let me just illustrate what I mean by this. Okay, so total variance, okay, is, I mean, if you want to compute this again, so you just see it here. You don't have to write it down here. Okay, so this is going to be 1 over n times, okay, so the sum of the squares here of the observations minus, okay, and then here you have the arithmetic mean, and then you take the square of it. Okay, so the mean of the squares minus the square of the mean. That's the variance, or let's say the total variance of y. Okay. Now, what would be basically the explained variance? The explained variance is basically the sample variance of the explained parts. Okay, so basically what you would do is, okay, so you would take the mean of the squares minus the square of the mean. That's going to be the same thing, but except that you don't have the total observations, okay, you only take the explained parts of the observation. So here you have y hat, okay, so y hat squared, okay, from I is equal to 1 to n. And then, of course, the mean of that. Okay, now, of course, since the means are equal, okay, so here in the previous statement, the means are equal, you see? So the mean of the total part is equal to the mean of the explained parts of the observation. Then basically you can just replace that by the mean of the total parts, because they are equal, okay? And in particular, you have the square of that, so you have the square of the mean of the total parts, okay? And what is the variance of the residuals? Okay, now since, I mean, the mean, I mean, here you have basically that the mean of the squares minus the square of the mean. Okay, so the mean of the squares is going to be equal to, and this is going to be the mean of the squares. That's epsilon I hat squared. This is the mean of the squares, right? And the mean of the squares is basically minus the square of the mean. That's going to be, now what is the square of the mean? Now guys, here you see this, that the mean is equal to 0, right? Because the variance, the mean of the total part of the y is going to be equal to the mean of the explained part of y, so the mean of the unexplained part must be equal to 0. So basically you would have that mean of minus 0 squared, which can be omitted, of course, okay? So I just omit this, and that's going to be it, okay? Or you can also write it differently. So you have 1 over n times the sum of the squares, okay? And then here you have, I mean, the residual part is basically equal to the difference of the total part minus the explained part. Okay, so if you subtract the total part from, if you subtract the explained part from the total part, and basically you would get the part that it's not explained, okay, by the regression model. So basically this is going to be it, okay? And this is also called the residual sum of squares. Okay, so this here, okay, that expression, or basically this is the same, okay, this one, or in particular this one, this is called the residual sum of squares, okay? Residual sum of squares, okay? Okay? Residual sum of squares is also denoted as RSS. Okay, so I think sometimes in EVUs, or maybe I'm not sure. Okay, so they use this notation here, RSS, meaning this is going to be the residual sum of squares. I mean, in the previous setup, we had to just, if you divide this by n, then you're going to get the variance of the unexplained part, or the residual variance. Okay, and then here you have the residual sum of squares. Now, okay, so here for this expression, okay, you call this is the explained sum of squares, okay? Because this is part of the explained variance, okay? So for that they use the notation ESS, okay? So this is for that ESS, okay? So meaning that you have the explained, okay? So the explained sum of squares, and finally here this is going to be the total sum of squares. Okay, so that's called TSS. All right. So in the software. Okay, but this is just basic information here. Okay, so on the other hand, you would basically get that the total sum of squares is going to be equal to the explained sum of squares plus the residual sum of squares. That's also going to be the same thing, because if the variance can be decomposed by that, then you would multiply the equation with the variances, then this is what you would get. Okay, so the total sum of squares is equal to the explained sum of squares plus the residual sum of squares. Okay. Now, of course, so since this is called decomposition of the variance. Now, what we are usually interested in is what is the ratio of the variance of y that can be explained, right? So basically, here we divide basically. Okay, so let's just go back to this equation. Okay, so what we have here is basically so the total variance equals the explained variance plus the residual variance. Okay, so that's what we were. Okay, and if we divide both sides of the equation by the total variance, okay, then on the left hand side of the equation we get 1, and on the right hand side we get basically this is, okay, so the ratio of the variance that can be explained by the explanatory variable, okay? And this is going to be the ratio of the variance that cannot be explained by the explanatory variable, okay? And this expression here is the so-called coefficient of termination, okay? Okay, so the coefficient of determination is basically, and this was part of the first assignment, I hope you remember. So the coefficient of determination is basically the ratio of the explained variance and the total variance. Okay, so that will, let's say it's going to be equal to 60%. That means that 60% of the variance of the dependent variable can be explained by the explanatory variable or by using the regression model. Okay, so by means of the regression model. Either way. Okay? Remember, coefficient of determination. Okay? So this is the coefficient of determination. Okay? Of determination. And this is going to be equal to, and that was, okay, so the variance of the explained parts divided by the variance of the unexplained parts, or basically 1 minus the variance of the, variance of the total parts here, 1 minus the ratio of the variance of the unexplained parts. Okay, so here you have the residual variance, and here you have basically the total variance. Okay, or you can use the TSS stuff, right? So you can also use that. So you have the explained sum of squares divided by the total sum of squares, which is also equal to 1 minus the residual sum of squares divided by the total sum of squares. Okay, so that's equivalent basically. Okay. All right. Now in your first assignment, you had to prove that this is equal to, in this setup, if the condition of expectation, remember that, so if the condition of expectation of basically of the dependent variable is a linear transformation of the explanatory variable, okay, so then basically the coefficient of determination is equal to the square of the correlation coefficient, right? Remember that? Okay, so that was a statement that we had, so I'm gonna summarize that. So for a simple linear regression model, okay? Okay? I mean, guys, simplicity means that there is just one explanatory variable. Okay, so simple doesn't mean that it's easy to calculate. Okay, so it means that there is just one explanatory variable, guys. Okay, so simple linear regression model we have. okay? Basically that the coefficient of determination is equal to the square of the correlation coefficient, okay? And the correlation coefficient is, and this is what you also see, the covariance divided by the product of the standard deviations, okay? Right? So this is what you would do, okay? Right? Remember this? Okay. Now, okay, so based on that, and we'll continue, okay, so that's how you calculate the coefficient determination. Okay, so if you continue, then we're going to get the following. So here you see, I mean, this is, okay, so the variance of the error term is going to be sigma squared. So this is going to be the variance of the noise, okay, so of the error term. The theoretical variance, okay, not the empirical one. And estimated for that, okay, will be as follows. So the estimator is going to be, and then here you have it, okay, so this is going to be sigma squared hat, okay. So basically you would, I mean, the sample analog would be here, okay, so this is, I'm not talking about this is not the variance or the residual variance, okay? This is not the residual variance, but this is going to be the estimator. And for the estimator, you'll have that this is going to be equal to 1 over n minus 2 times the residual sum of squares, okay? So that's going to be the estimator for that, okay? Why n minus 2? Because you have two parameters that need to be estimated, okay? Okay, so here you have, okay, so this is 2, this is the number of estimated parameters, okay? And why do we have 2 parameters? Because of course, we have A and B, we have the slope, and we have the intercept that we need to estimate for that. Okay? So maybe remember this. Number of observations minus the number of estimated parameters will give you the degrees of freedom. Okay? So number of estimated parameters, okay? So here you have A and B, the intercept and the slope, okay? That all need to be estimated. Okay? And n minus the number of estimated parameters is going to be equal to the degrees of freedom. Okay, so you have n minus 2 degrees of freedom here. Okay. Why do you divide this by n minus 2? Maybe remember this, because the estimator is unbiased otherwise. I mean, no, this is not. This is unbiased here. But if you don't divide this by n minus 2, you choose to divide this by n, then you would get a biased estimator. Okay, so maybe remember this, that the expectation. Okay, so the expectation here of this estimator is going to be equal to the theoretical variance of the disturbance term. Okay, so that's how it's going to be estimated. Okay? Okay. So this is unbiasedness. Okay? So unbiasedness. Good. Okay? I hope that you remember this. Okay? Now, how would you estimate basically the test statistics, okay, or how would you estimate the variances of the basically of A and B. Okay, so the estimates, estimates of variances. Okay, so how would you estimate the variances? Okay, so for the regression coefficients, and I'm going to start with this. Okay, so the estimator for the variance, okay, for the coefficient beta. Okay, so I'm using that notation. This is going to be the estimate of the variance of the coefficient beta. This is going to be equal to the estimator of the variance, or the variance estimator, let's say, of the error term, times 1 over n times the variance of x. Okay, so the variance of the explanatory variable. Okay, so this is the estimate of the variance of the slope. Sorry, this is b, not beta. This is b. Okay. Okay, I use a different notation. And the estimate of the variance of I will be equal to, this is going to be equal to sigma squared hat, okay, so the variance of the estimator of the error term, times, okay, and here you have the following expression. This is a little bit weird. So here in the denominator, you'll have n times the variance, the empirical variance of x, okay? Alright, so this is going to be the first step. And here in the numerator you have the mean of the squares of x. Okay, so here you have the mean of the squares of x. Okay, so this is the mean of the squares of x. That's what you have basically in the numerator. Okay, of course, I mean these things cancel out, so but you don't need to take care of that here. Okay. So these are basically the formulas. So the interpretation for that is, this is going to be equal to, I mean, that was the standard error of regression. Okay. So sigma hat is the standard error of the regression. Okay. There are multiple interpretations for that. So that could be also, for instance, the forecast error. So let's say you want to suppose that you want to use the regression model for forecasting, okay? So that would be the mean of the forecast error. This is what you would have, okay? So this is the mean, okay? So this is the mean of the forecast error, okay? So the forecast error, provided that you wish to use the regression model for forecasting. Okay, so that's the interpretation, okay? Now, basically the square root here, okay, of the slope, I mean of the variance estimated for the coefficient is going to be the standard error of B. Okay, so that's how it's called. This is the standard error of B. Okay, so an interpretation would be this is the estimation error. Okay, so the average, the mean of the estimation error. Okay, this is the standard error of B, and similarly, this is going to be the standard error. Okay, standard error of A. Okay, we also use the notation SE. Okay, so for the standard error. Okay, sometimes I use that as well, so to make things a little bit easier. Okay, so standard error of basically of B and the standard error of A. Okay? So this is the mean of the estimation error. Okay, so the estimated mean of the estimation error. Okay? And of course, based on that, we're gonna look at some tests, but okay, so let's just stop here and then we just look at the autoregressive process. Okay, so let me just give you a mark. Okay, so the autoregressive process. Okay, so if you have first order autoregressive process, okay, basically you have yt is equal to the constant plus a times yt minus 1 plus the noise, okay? Then you can use this, or the coefficients a and v can be estimated by means of the all-S regression, okay? So basically you have, okay, that v and a can be estimated by OLS regression, okay? So by just using the ordinary least squares method, okay? But you have to adjust the formulas, guys, okay? Because here in this case, this is going to be the dependent variable, okay? So this is the dependent variable, right? And that's going to be, this one is going to be the explanatory variable. Okay? So in the previous setup, I called the dependent variable y and the explanatory variable x, but here it's different. This is different, right? Okay? Now let's see what I mean by this, and maybe you can, or we can look at the exercise 5.4. Okay, so just a little example, just to illustrate what the computer does. Okay, so basically I'm going to suppose that you have, okay, so it's going to be something that you observe here, okay, and assume that basically these are observations of a first order autoregressive model. Okay, so what I mean by that is, let's say time. Okay, so here let's say you have a time. Okay, so time at equal at 1, 2, 3, 4, 5, and 6. Okay, so you have 6 observations, and the observations of the process are 0, 3, 5, 2, 0, and 5. Okay, whatever the reason might be. Okay, so these are the observations. And suppose that these observations are observations from a first order autoregressive process. Okay, so this is what you would have for the process. Okay, now what is basically the explanatory variable and what is the dependent variable? I mean, if you have, let's say, basically the equation is equal to, or yt is equal to v plus a times yt minus 1, then basically what would be the sample, okay, of the explained variable? Okay, so let's say you have time t here, okay, and you have 1, 2, 3, 4, 5, and 6, okay, so that's going to be the time, the points of time to be precise, okay. So let's say here you have the observations yt. Okay, so this is the dependent variable, and this is the dependent variable, and here you have the observations of the explanatory variable. Okay. Now, guys, if the first observation is basically 0. Okay, so or let's say that goes the other way around. Okay. Then you would have here basically the previous observation, right? But the previous observation is not there. Okay? So this is not there because that would be the observation at point 0. Okay? It's not there. What is the observation at point 2? Okay, now the observation at point 2 is equal to 3, right? Okay? Now what is the observation here at point 2 minus 1, and 2 minus 1 is equal to 1, so this is going to be equal to 0, right? That's how it works. You understand? Okay, so that's the first, second, the third, etc., etc. Okay? Now what about the third observation? The third observation is going to be 5, right? The fourth, the previous one is going to be 3, right? So here, basically just a sample, you have shifted the sample here. You understand? Okay? I mean, it depends how you're going to look at it, but this is how it works. Okay? So here at point 4, you have, this is going to be equal to 2. Alright? And at point 3, which is the previous one, is going to be equal to 5. at point 5 is going to be equal to 0. Right? So then at point 4 is going to be equal to 2. Alright? And then what you will have is the 6th observation is going to be equal to 5. Okay? And the previous one is equal to 0. Okay? So you have to be careful. Okay? Because here in particular, you have 6 observations of the time series. Okay? So capital T is equal to 6, right? So we have 6 observations of the time series. Okay? But how many observations do we have regarding the pairs? You have just 5 observations. Okay? So you have to be careful. Alright? Because you just have 5 observation pairs to be, if you want to be precise. Okay? And here, you could continue the table, right? So there is no such thing as a 7th observation, but here you have still the 6th observation, which is going to be equal to 5. So basically the samples are just shifted here. Okay? Alright? It depends how you would, how you would assign the values here for that. But you have to be careful. Okay? So that goes from 1 to the 6th, right? So this sample, and that's going to be the other one. Okay? So you just have 5 observation pairs. Okay? You have to be careful. Okay, so I'm going to focus on these 5 observation pairs, right? Okay. That's the one, that's a sample that you would take. Okay? These are the observation pairs. Okay? So that's how you would basically adjust the formula. Okay? Alright? Now, if you want to transform this, this is, okay, so in the previous setup, this was equal to y and this was equal to x. Okay? That's how you would do it. Okay? So that's where it starts. Okay? So you just have to be careful. Okay, now the question is how would you calculate basically the estimators here for that? Okay, now first off you need to calculate the sample mean of the dependent variable. Okay, so the sample mean of the dependent variable, I'm going to call this t minus 1, t by t bar. Okay, so this is going to be the sample mean of the dependent variable. So you just have 1 over 5 instead of 1 over 6, right? So 1 over 5 times 3 plus 5 plus 2 plus 0 plus 5. Okay. You have to be careful. Okay. And